In this video, I'm going to talk about the backpropagation through time algorithm. That's the standard way to train a recurrent neural network. The algorithm is really quite simple once you've seen the equivalence between a recurrent neural network and a feed-forward neural network that has one layer for each time step. I'll also talk about ways of providing input and desired outputs to recurrent neural networks. So the diagram shows a simple recurrent net with three interconnected neurons. We're going to assume there's a time delay of 1 in using each of those connections, and that the network runs in discrete time. So there's a clock that has integer ticks. The key to understanding how to train a recurrent network is to see that a recurrent network is really just the same as a feed-forward network, where you've expanded the recurrent network in time. So the recurrent network starts off in some initial state, shown at the bottom there, time 0, and then it uses the weights on its connections to get a new state, shown at time 1. It then uses the same weights again to get another new state, and it uses the same weights again to get another new state, and so on. So it's really just a layered feed-forward network where the weights are constrained to be the same at every layer. Now, backprop is good at learning when there are weight constraints. We saw this for convolutional nets, and just to remind you, we can actually incorporate any linear constraint quite easily in backprop. So we compute the gradients as usual, as if the weights were not constrained, and then we modify the gradients so that we maintain the constraints. So if we want W1 to equal W2, we start off with them equal, and then we need to make sure that the change in W1 is equal to the change in W2, and we do that by simply taking the derivative of the error with respect to W1, the derivative with respect to W2, and adding or averaging them, and then applying the same quantity for updating both W1 and W2. So if the weights started off satisfying the constraints, they'll continue to satisfy the constraints. The backpropagation through time algorithm is just the name for what happens when you think of a recurrent net as a layered feed-forward net with shared weights and you train it with backpropagation. So we can think of that algorithm in the time domain. The forward pass builds up a stack of activities at each time slice, and the backward pass peels activities off that stack and computes error derivatives each time step backwards. That's why it's called backpropagation through time. After the backward pass, we can add together the derivatives at all the different time steps for each particular weight, and then change all the copies of that weight by the same amount, which is proportional to the sum or average of all those derivatives. There's an irritating extra issue. If we don't specify the initial state of all the units, for example if some of them are hidden or output units, then we have to start them off in some particular state. We could just fix those initial states to have some default value like 0.5, but that might make the system work not quite as well as it would otherwise work if it had some more sensible initial value. So we can actually learn the initial states. We treat them like parameters rather than activities, and we learn them the same way as we learn the weights. We start off with an initial random guess for the initial states, that is, the initial states of all the units that aren't input units, and then at the end of each training sequence we backpropagate through time all the way back to the initial states, and that gives us the gradient of the error function with respect to the initial state. We then just adjust the initial states by following that gradient. We go downhill in the gradient, and that gives us new initial states that are slightly different. There's many ways in which we can provide the input to a recurrent neural net. We could, for example, specify the initial state of all the units. That's the most natural thing to do when we think of a recurrent net like a feed-forward net with constrained weights. We could specify the initial state of just a subset of the units, or we could specify the states at every time step of a subset of the units. And that's probably the most natural way to input sequential data, Similarly, there's many ways we can specify the targets for a recurrent network. When we think of it as a feed-forward network with constrained weights, the natural thing to do is to specify the desired final states for all of the units. If we're trying to train it to settle to some attractor, we might want to specify the desired states not just for the final time step, but for several time steps. That will cause it to actually settle down there rather than passing through some state and going off somewhere else. So by specifying several states at the end, we can force it to learn attractors. And it's quite easy, as we back propagate, to add in derivatives that we get from each time step. So the back propagation starts at the top with the derivatives for the final time step, and then as we go back through the layer before the top, we add in the derivatives for that layer, and so on. So it's really very little extra effort to have derivatives at many different layers. Or we could specify the desired activity of a subset of units which we might think of as output units. And that's a very natural way to train a recurrent neural network that is meant to be providing a continuous output.